I'm going to start this video off as I usually do when doing documentaries on Heathkit test equipment products by looking at Chuck Penson's excellent book, Heathkit Test Equipment Products. Digital Frequency Counters and Multimeters chapter. To get past all the ones I've already done, all the Nixie tube based ones, and then lots of their early digital multimeters. And then we get back into frequency counters again with the IM-4100. All the earlier ones are called IB, but later on Heathkit started using the IM prefix for both digital multimeters and frequency counters. And then the rest of this chapter is on the frequency counters. The subject of this video is the IM-4100, which came out in 1975 and was discontinued in 1979. I think I bought mine in 78, probably. At least I was going to college in those years, and I know I bought this and used the college's laboratory as a frequency standard to calibrate it so I could get the best possible calibration. It cost $139.95, and Chuck Penson says the 30 megahertz IM-4100 marked Heath's transition from the old technology of cold cathode displays, that's Nixie tubes, to modern LEDs. The most significant benefit from this was a vastly reduced parts count and the attendant reduction in cost. The IM-4100 has three modes of operation: measuring frequency, measuring period, in other words the length of time between two events, and totalizing, in other words counting events. Frequency range from 5 Hz up to 30 megahertz. The sensitivity is 15 millivolts, so it can register any input from that level on up. The period can be measured from 1 milliseconds to 99.999 seconds. Low frequency, blah blah blah. The period can also be used for very low frequency measurements by switching the time base to the MS position and the mode switch to period. You have to manually solve for frequency using the formula. Input impedance is 1 mega ohm. The totalizer can go up to the full 5 digits, 99.999 or 99,999. An inhibit signal can be applied through the rear panel to stop the count without loss of displayed total. Replaced by the IM-2400 series. In other words, these meters here. It's really kind of odd to say that because there is no IM-2400 series. It's this meter here, period. I mean, this is IM-2420, but it's a very different style meter. This is the only one that's really a replacement for this one. It is, of course, a screamer by comparison. It goes all the way up to 225 megahertz. Anyway, so that's the thing we're going to be talking about here. Of all the vintage Heathkits I have, and I'm referring primarily to test equipment, although I do have other products of theirs still, my original home electronics lab test equipment was all Heathkit, and I still have some remnants of that. The oldest one is this IM-4100, which is just a very basic low-end LED display frequency counter. And I built this when I was still finishing up my college, and got good use out of it, and I've still used it occasionally, even though my primary frequency counter is this BK Precision 1823A, which is a 2.4 gigahertz unit, and it's actually a triple counter, all with one display, but you can have 3 counts going on at the same time. Occasionally I would still find the desire to have an additional counter, or one that was just, I don't know, just out of perverse reasons to use it. And it's always worked, and whenever I've compared it to reference signals, its calibration was good. And I still have this 2240 digital LC bridge that I use quite a lot. And then a very occasionally used 1277. During this period of time, Heath was liking to call himself Heath instead of Heathkit on their test equipments. And they were leaving off the prefix. So, you know, it might be an IM-4240, but they would call it just the 2240. That was a thing they were doing at that time. Now, these things still work and get good use. Certainly the LC bridge gets used a lot more than the pulse generator does. And I'd actually bought that because I was doing some consulting work like 30 years ago where I needed to have a reliable pulse source for something I was designing, and my signal generator wasn't good enough for the application. And this was much more, it was easier to dial in exactly what I wanted. And I used it that one time and then very rarely since then. I have good reason to believe it still works because occasionally I hook it up just to see if it still works. Anyway, so these are the 3 pieces of Heathkit that I built myself and still have and still use. But the last time when I was troubleshooting one of the earlier Heathkit IB series Nixie tube display frequency counters, and at the same time doing an introduction on this inexpensive digital signal generator for a YouTube video, I hooked it up to this and realized it wasn't making any display for inputs. And so I decided this was a good chance to do a quasi-restoration on this. Open it up, do a quick video on it, hopefully a quick video, and also see if I can get it working again. Now this is interesting. All 4 of the 3M bump-on feet that were on here have drifted to the front. Just slid like little glaciers. And I think the reason for that is that my stack of equipment gradually leans back more and more, since the front bezels are taller than the rest of them, and each one sitting on top of another one. They just progressively angle back more and more. And this one was at the top of the stack. It was up where this thing goes now, and I guess that was enough to just, and it's pretty heavy, and those feet are grippy, and I think it just slowly walked its way backwards. The adhesive it's strong, but it's not designed to have unrelenting forward or sideways pressure. The shear grip of the adhesive is not good. It's good if you just try to pull them off, but it's obviously not ideal in the shear direction. I'm going to end up replacing those feet. The case cover comes off with 2 screws on the bottom, and these are machine screws, not sheet metal screws. And then 2 more at the upper rear corners, also machine screws. And to Heathkit's credit, they're using PEM nuts on these instead of just threading them into tapped holes in the case. Same thing for those screws that come in from the bottom. That's something Heathkit finally started to do in the later years. Before that, it was pretty much always just sheet metal screws going through into self-tapped holes in the chassis. So anyway, what do I have in here? I've got some connectors for some reason. And some a spare fuse. Okay. Anyway, I'm going to just hook it up again and see if maybe it was a fluke that it wasn't working before, and maybe it'll work now. Alright, let's turn this guy on. I'll turn it up to the first position. There are only 2 choices here, the kilohertz or megahertz mode. So if you're looking at it from a a gate time, you either have a, I guess it's a 1 millisecond, doesn't say so, but that or second time base, which is also putting it in kilohertz or megahertz mode. And then you have a mode, which the earlier ones, the earlier frequency counters that Heathkit put out did not have this. Normally you'd have it in frequency counter mode. You can also do it in period mode, where it swaps the two inputs to the counter circuit. So remember that any frequency counter has the input signal, which has been conditioned from whatever it is to a logic level signal and made into a square wave before it gets into the counter circuit. You've got that signal, and you've also got the very precise square wave type of gate signal, which admits the input signal to the counter chain. Now if you reverse those two, so the gate signal now influences the input and the input now acts as the gate signal, you can turn it into a period counter, where it's telling you the period between two pulses, for example. Or you can put it in totalized mode, where you're not using the gate at all. Switch is a little sticky here. In the totalized mode, you're just using the counter by itself without the time base, and it's just counting inputs. And it'll keep counting inputs until you stop the inputs or push the reset button to reset it back to 0. And that's very useful and a very simple thing to do. It's always kind of amazed me that as easy it is to do this, earlier frequency counters didn't seem to have it. At least Heathkit ones didn't. And then you've got an input attenuator, so it doesn't have a very sophisticated front-end circuit here to adjust for input levels. So it's working more on an attenuator basis. You don't attenuate it at all, or you attenuate it to a 1/10, or you attenuate it to a 1/100th. For logic level signals, I think 1 should be about right. And I have my counter set up with a 1 kilohertz sine wave, 4 volt peak to peak, which should be a good general value. So let's turn this guy on. The gate is working, but there's no signal. But I haven't turned the signal generator on yet. How about that? So I'll turn the signal generator on. Oh. Well, it's reading a number, but it's not the right number. It is not showing 1 kilohertz. Now we know from the switch position that it should be showing us kilohertz, 1 point something, but I'm giving it a 1 kilohertz signal. That suggests to me that the signal is under attenuated. So maybe if I add a little attenuation, it'll clean up. There we go. It's working just fine now. Maybe the switches just needed a little motion or something, because it's working perfectly. Let's give it a different signal. I'm going to go up to 6 kilohertz. And that's pretty much right on the money. All counters are plus or minus 1 digit at best. So that last digit that bounces around, that's inevitable for a regular frequency counter. And that's due to the asynchronous nature of the clock signal and the input. Just depends where the input pulses fall relative to the clock. You can always gain or lose one of the pulses depending on where they are, positionally speaking. Let's go up to, I don't know what the maximum of this is. I don't think it's very high. Let's try going up to 20 kilohertz. Well, it's doing that. Right on the money. It's doing 30. No problem. It's doing 50. But this is only kilohertz. This isn't very fast. I'd expect this to have problems if I get into the megahertz range. So 90 kilohertz. Now we're into megahertz, and it's right on the edge of going over, but it's not indicating over. So now I've got this extra decimal point that popped up next to the over legend, so now it's indicating an over. It's trying to show a 1 in this extra position, so it would be 1, and if you round all these 9s up, it would be a 1 here, so 1.1 megahertz, which is exactly what the generator's putting out. So we're really quite accurate here. You know, it's within 2 least significant digits, and if that rolled up that much, it would be actually displaying the 1.1 megahertz, except it can't display the top value because it's off of the display, and that's why we have the indicator here. So now we can switch to megahertz mode. I have to read the manual again. Maybe that decimal point is fixed. How much we forget when we don't use things. So I'm giving it 10 megahertz now, and it is reading it correctly. I am now giving it 10 megahertz, and if I go over and take it down to 5 megahertz, that's correct. 1 megahertz. So we'll go back here and we'll go up to, yeah, my generator won't go higher than 25 megahertz. But I know that this counter can go higher than that. But anyway, it seems to be working just fine. If I go to the 100 attenuation, it's still working fine. So obviously its native input is capable of handling very small signals, like maybe you'd get if you're poking around in a radio receiver or an audio device and you're dealing with fractional volt signals, quite possibly quite low voltages. The front end of this is apparently able to respond to those. That's when you would have it in the 0 or the 1 attenuator. And for higher signals, like the logic signals that are being dealt with here, you can be in the full attenuation mode, and it's still an adequate signal to get it up to where it needs to be. I'm going to go back to 1 kilohertz here. So now it's still trying to show that in megahertz. 1 megahertz would be here. This would be 100 kilohertz, 10 kilohertz, 1 kilohertz, and because it's always plus or minus 1 least significant digit, it's really unstable here because it makes it look like it's jumping more than it really is. So we'll go back down to kilohertz, give it 1 gate period, and it's back to 1.000 kilohertz. So let's go down to something really low. I'm gonna change my input frequency to 2 hertz. Boom, there it is, plus or minus 1. So that is 1 kilohertz would be out here, so 100 hertz, 10 hertz, 1 hertz, or rolling over to 2. So now that we're pretty low, let's put it over in period mode. Had to move the attenuator switch to get a more stable display. So it's basically 0.1 second, and even though the math is pretty easy to do in your head, let's just use the old calculator here. 0.1 second and take the reciprocal of that. That's switching period to frequency, and it's 10 hertz, which is of course exactly what I'm giving it here. So the period mode certainly works. I'm going to go back, I'm at 10 Hertz, right, so I'm going to go back to 1 Hertz. So 1 Hertz, that's 1 pulse per second. And I'm going to switch it to totalize mode. And now we have a clock counting up 1 count per second. So the totalize mode works that way. And I can reset it whenever I want and start it again. For this, the time base doesn't change because the gate circuit is out of the picture here when we're in totalize mode. So what if I put in 1 kilohertz here? Just for fun, let's go to 1 megahertz. No, that'll be too high. Let's go to 500 kilohertz. So we've already overranged, obviously. Even if I reset it, it's boom, just like that. So let's go to something a little less colorful and more reasonable. Let's try 20 kilohertz. I think we still won't. Yeah, we can watch that one work. It doesn't take very long to get an overrange. Yep, so I'd say this guy's working just fine. Don't know what the problem was before, but it was probably related to switches just not making good contact due to infrequent use. I just did a quick check of the electrolytic in here, both ESR and DCR. It's not ideal to do it in circuit, but this is a very simple circuit. It looked like it should be a reliable test, and it's showing that this cap is still quite good. So normally I would replace these, but since my goal was not to do a restoration on this, I decided to leave it where it was. I have done some cleanup. I've gone over it with alcohol wipes and cleaned everything up. And I removed the feet with some adhesive remover, and I'm going to put on some new 3M bump-on feet. Same style and size, just different color from the originals. And there those are in the original manual specified positions. Alright, there's the beauty shot. Alright, let's do a tour of the frequency counter with the chassis open. I'm going to start with the rear panel. You have the power cord coming in, of course. There's a hole to stick a screwdriver through into a trim capacitor to slightly tweak the internal oscillator frequency. The internal-external oscillator switch and the input-output jacks on the rear are used together in a variety of ways. If you're in the frequency counter mode or the period measuring mode, the main time-based counter chain can utilize either the internal 1 megahertz oscillator. It's really a 10 megahertz oscillator divided down to 1 megahertz, but that 1 megahertz is the master clock. Or you can input a more accurate 1 megahertz TTL level clock in the back and use that instead of the internal one. And that'll all just depend on the setting of this switch. In the external position, the internal crystal oscillator is disconnected from the master clock counter chain, and therefore the signal can be overdriven or overridden by the externally applied one. When you're in the internal clock mode, then that clock is applied to these as an output. So you can get external access to the internal 1 megahertz clock, which again is the 10 megahertz crystal oscillator divided by 10. If you're in the totalized mode instead of the frequency or period modes, then these jacks do something different, and you still have to select this to external, and you can connect anything up here. It could be a switch, it could be a TTL logic signal, but the totalized mode counts input pulses coming in through the normal input jacks, and it keeps counting them indefinitely until you either overflow the counter, or you reset it, or you stop it, either permanently or temporarily. And that's what these jacks are used for in that case. Let's say you had a count going in the totalizer mode, but you want to suspend that count for a while. You could have a switch connect this jack to this jack, thereby shorting this to ground, and that would freeze the count. It won't accumulate anymore, but it won't lose the count it already has. And then when you open the switch, it could continue counting again. Or you could drive it again from a TTL source that is a logic 1 when you want to allow totalized counting to occur, or make it logic 0 when you wanted to freeze or suspend totalized counting. So that's how that all works. During this period of time, Heathkit was making a lot of their smaller bench test equipment set up so it could be used in a mobile application. So in addition to the normal AC power, there was this external jack here which allowed you to provide a typical 12 volt DC power source. You have a ground, you've got the plus and minus connectors or pins on here for connecting, something like an automotive or a boat electrical system to this to power it. And this power jack is just diode coupled into the output of the bridge rectifier on the inside of the normal power supply. So either rectifier can be coupled into the voltage regulator circuitry, and you could use either one. It does require a fairly high current, 1.25 amps, so you'd have to run it off of something again like an automotive system, because that would drain a lot of regular 12 volt batteries pretty quickly unless they're being driven by a generator or alternator type circuit. I'm going to go over the front panel here. It's a little bit redundant to what I cover elsewhere in the video, but I just want to cover it while I'm on this part of the overview. So the front panel switch is power off in the leftmost position, and depending on if you're in frequency or period mode, you can have the time base set for 1 kilohertz or 1 megahertz. That would be for the frequency counter function, or 1 second or 1 millisecond for the time base if you're in the period measuring function. If you're in the totalizer function, this doesn't make any difference, and you just want to turn it to either of those two positions besides the off. Once again, the period input, while you could sort of generically use that to just measure the period of things, in practical use it's a little more specific than that. When you have very low frequencies, say you're trying to measure only a 10 hertz signal, the frequency counter mode is going to give you just a 1 and a 0 on the, well, it's going to be kilohertz, so the display is going to have a decimal point after the second digit, so it's going to be capable of displaying 1.000 kilohertz, which means, yes, only the most or the least significant two digits are going to display the 1 and the 0 of that 10 hertz input signal, which is really poor resolution. And if you're really trying to get that accurate, maybe you care whether it's 10.000 0.05 hertz or 10.03 hertz, you wouldn't know because it'll be off the right of where the display can indicate. In situations like that, you can turn the frequency counter on its head and put it in period mode, and now the circuitry works to give you a much higher resolution display for those low frequency signals. So that's really where the period mode comes in. You still have to do some math because now you've got the period. You need to take the reciprocal of the period, and then you find out the frequency from that. But it's very useful to have. And then finally, the input attenuator. Basically, the manual doesn't describe it at all anywhere I could see. You would think you would start out in the 1 and then go up to the higher ones if you've got a higher voltage, but it seems like what you really need to do is start out with it in the most attenuated position and see if you get a reading, and if you don't, then decrease the attenuation until you do. In the demo I do in this video, I started out with it in 1, and I was getting, instead of a 1 kilohertz display, I was getting like 1.4 kilohertz. Well, if I didn't know any better, I would just assume I'm giving it a 1.4 kilohertz signal, and the counter's telling me the truth. But in fact, I knew it was a 1 kilohertz signal, so I knew to go over here and change the attenuation. Well, what if you don't know what your input frequency is? By the methodology I used in my demo, you would never know. But if you started at the high attenuation, didn't get a display, and went down to 10 and got a display, then you can trust that. And you might want to go down to 1 then and see if it changes, and if it doesn't, well, great, that's even more confidence. But if the count increases when you go to 1 from 10, then you can be pretty sure you're just picking up noise, and you should go back to 10 when you get a stable reading. Anyway, that's how that gets used. And if you're in the totalizer function, then you have this reset button. It's a momentary push button, and it'll just count up until you either stop the input signal or reset it with the button, at which point it'll start again as long as there's still input pulses coming in. And you have the one and only jack, which provides the input signal. It's a BNC jack. The input voltage rating on this, in lower frequencies, all the way up to 100 kilohertz actually, this can tolerate up to 250 volts RMS, beyond which it's not advisable to go, and the protection circuitry should protect it, but you could possibly get into a damaged situation, especially if you sustained that for a long period of time. All the way up to 100 kilohertz, you can apply that kind of voltage to it, or anything way down from 250 volts RMS down to, very fractional voltages, and it'll still work. Once you get above 100 kilohertz, all the way up to the rated 30 megahertz of this counter, the maximum voltage rolls off fairly sharply. And depending on what your attenuator setting is, it rolls off at a different rate, but regardless, once you get up around 30 megahertz, the maximum voltage is only, I want to say about 24 volts. I don't have that in front of me, but I think it's about that. So definitely a lot lower than you would have in the lower frequencies. But again, for most circuits you're liable to use this with, if you're up in the megahertz ranges, your signals probably aren't going to be that high a voltage anyway. So here's a look under the circuit board. There's your external internal oscillator switch with wiring that just goes around and comes in on the bottom of the circuit board somewhere a ways away from where the switch is. The bottom of the power transformer's down there. There are some wires coming off of a wiring harness. It's actually a split ribbon cable, but it acts like a wiring harness. That's coming from things on the front panel, and some points connect up and around here. Other wires connected other places down there. There's a tangle of wires around the main power switch. The two brown wires are the AC power leads coming to that, and that's why there's extra space between the two rows of contacts on the switch, because the upper two rows are for low voltage DC and the bottom row is for the higher AC voltages coming in from the power line. And there's a piece of fish paper jammed in there because it's quite close to the chassis. Then of course the other wires going into the back of that switch are just what's needed for use by the logic. And then of course back there where it's really hard to see are additional wires for the other two switches, and they all make their way to the bottom of the circuit board in various places. There's the BNC jack, and its ground lead goes straight up to the bottom of the circuit board on that yellow lead, whereas the middle or the center of the jack goes through a red wire down below, and it goes over to the attenuator switch, which is the next switch next to it. And there are 3 resistors for attenuation, each with a capacitor in parallel with them, all tied right onto the back of the switch. You can see at least one of the resistors up there with its color stripes. You can see a couple of the disc capacitors easily. Another one back there a bit further. Those are all the attenuator circuit components. And then the signal comes back with the orange wire that goes up into the circuit board right next to the yellow wire. So that's where the signal, the input signal, enters the circuit board. And here's more of that ribbon cable that's connecting things around. The only other thing down here is the 7805 linear voltage regulator IC, which is using the bottom of the case as the heatsink. Heathkit did something here which I appreciate. Instead of soldering wires on the circuit board directly to the pins, which would require disassembling the regulator from the chassis, and that means interrupting its insulator and its other components that might not be as good once you put it back on, the 7805 can remain attached to the chassis, and you just unplug that little Molex plug from its pins whenever you want to lift the circuit board out of the chassis for repair or whatever. Alright, let's look at the power supply. We come in through the power cord, and it does go right to the circuit board. And the brown wires for the power switch leave the circuit board, run under the circuit board, and go to the switches I showed earlier. Unlike a lot of Heathkit equipment, this one has a voltage selector switch. The majority of their products, in my experience, require you to wire up the power transformer one way or another with jumpers on the transformer itself. But every once in a while, whoever designed particular products said, no, that sucks, we should put a switch on there. And this is one of the ones that has the switch. So there that is. This big capacitor there is across the power line. And let's see, there's wiring from the DC power jack on the rear. There's your AC fuse, and there are the 4 diodes of the bridge rectifier that's used for the output of the power transformer, converting it to DC. There's your big filter capacitor that filters that rectified DC. And I believe that other diode, the one that's down there right next to the fuse, is the one that brings in, yeah, because the red wire from the AC or the DC power jack goes in right next to it. So you can visualize positive 12 volts DC coming in there, going straight over to the back side of the diode, and then coming out of that and going directly to the plus output of the diode bridge and merging with it right there. And right next to that is the positive side of the filter capacitor, so they all run together right in that spot. And then of course the wires for the voltage regulator leave the board right around this area and go down to the voltage regulator on the chassis. Here's the LED circuit board. It really is just there as a way to mount the 5 LED modules and bring their connections down to the circuit board, primarily to the 5 display driver ICs. Some of the connections, there's actually, because there's 7 segment displays, there are 7 wires per digit that need to get from this board to this board. 3 of them per digit are done with these short little ribbon cables, just jumping over the ICs and going down. And the remainder of the pins, 4 pins each, are done through circuit board foils that go up to this. It's not really a connector, it's just wires soldered from one circuit board to the other, right where they join together mechanically, and that holds the board up as well as makes the electrical connections. There's also 5 volts brought up to this current limiting resistor, which is used for the overrange indicator, and I believe that there's also, yeah, there's another resistor there which I can't see at the moment, which is there for the gate LED. And there's the gate LED. It's a separate LED that's not part of the 7 segment display modules. So somewhere on there is a resistor, or maybe the resistor is this one that's right there in the middle of the picture. That's more likely, actually. So let's look at the front end circuit, the analog circuit. I started on that before and then I got sidetracked. So the input signal comes in right there where it says A and B. It's upside down, but that's where it is. And it gets applied through a resistor. That's that 1 meg resistor there, with the capacitor across it. And then there are the 2 diodes. The 2 brownish orange diodes are the input protection diodes. So if the input gets too high, it'll clamp them to the signal to ground. It'll clamp the signal to ground, I meant to say. And then there's an FET right there. That's an FET, and that provides the input impedance conversion. So you have a very, very high input impedance on the FET, therefore it will not load down signals that you're connecting this up to. And this transistor there in the middle of the picture is a PNP transistor that's used in conjunction with the FET. It just helps it function in this application. And then really the whole rest of the front end circuit is a Schmitt trigger that is there to clean up the waveform. And that is done in 3 stages, and they're all part of this one IC, and it's an ECL type IC rather than TTL. So that makes it very fast, although somewhat power hungry. But this is a very traditional way of doing a frequency counter front end. That enhanced FET front end followed immediately by 3 stages of an ECL line driver, really, and each one of the stages does something different in the course of amplifying and attenuating and Schmitt triggering the signal. All of that is there because you need to take an input signal which can be very widely different in voltage, and also whether or not it's AC or DC, if it's AC with a DC component, if it's all AC or all DC. You know, there's a lot of permutations. I don't want to get my tongue tied up here, but a lot of permutations of the form a signal can come in as. And this chip's job is to even them all out and result with a nice clean TTL level signal. Because this is an ECL chip and its signal levels are different from TTL, these two transistors right there convert the ECL levels into TT compatible levels for use by everything else. And then we have the switches. These are really just ANDs and OR gates in these couple of ICs right in the middle of the picture. And because this is not just a frequency mode counter, and is also a period counter and a totalizer counter, you have to juggle the various signals in a few ways depending on which mode you've selected on the front panel. And all that's done by simple AND and OR logic, and those gates are all on these two ICs. Alright, let's look at the master clock. So way over here on the left we have a 10 megahertz crystal, and then this IC here is a quad NAND gate. 3 of the gates are being used as the oscillator support components for the crystal, and out of that you get the 10 megahertz TTL level signal. And this IC is a decade counter, and it takes the 10 megahertz TTL signal coming out of here, divides it down by 10, resulting in a 1 megahertz clock signal, which is used by a number of things in here, primarily the master clock counter chain. 6 ICs, they're all decade counters, just like this one is. But they're in a chain, and it starts out with that 1 megahertz signal, divides it by 10, so you get 100 kilohertz, divides it by 10 again, so you get 10 kilohertz, again to get 1 kilohertz, and that 1 kilohertz signal is important and is used in a few places in the circuit. Divided again, you get 100 hertz, divided again, you get 10 hertz, divide it one more time, you get 1 hertz. And that signal is also important, just like the 1 kilohertz signal was. So the function of all these ICs is just to turn the 1 megahertz signal into a 100 kilohertz signal and a 1 hertz signal. These 3 ICs work together to convert the 1 hertz or the 100 kilohertz signals from the master clock into the actual 1 second or 1 millisecond with pulses that are used as the gate signal, which admits the input signal coming from over here into the counter chain for display purposes. So that's what a lot of this is doing. And also from the gate signal are derived ancillary signals such as the transfer signal, which is used when you finish a count. In other words, when the gate signal goes away and the count stops, you have to immediately transfer the count contents into the display ICs, and that pulse is generated here. And then once you've done that, and after a short time delay, then the counters are all cleared in preparation for taking another count, I meant to say, and then the next gate signal will follow that. So it's open the gate for a specified period of time, allowing the count to accumulate, close the gate, immediately transfer the BCD contents from the counters into the display ICs, and follow that up with a clear to clear all these back to 0, and then come around and do another gate and repeat, repeat, repeat. This third IC is actually a monostable multivibrator. It's a pulse generator, because the signal that does the transfer, I think it's the transfer signal. No, it isn't. It's actually another signal downstream from that, needs to be a particular pulse width to work properly. So this takes the shorter transfer pulse generated from these ICs and turns it into a fairly accurate and consistent longer pulse width, which is necessary for some housekeeping operations inside the rest of the counter circuit. Now I'm touching on the same subject twice, once when I'm doing the demonstration and again now, but which order I edit them together I'm not sure yet, so one will come before the other, but maybe not the way I'm saying it now. These are kind of like a multiplexer, but really they're just a bunch of gates acting like switches. If you're in the frequency counter mode, you have to use the master clock to generate the gate that allows input signals into the counters. And if you're in the period mode, you need to do just the opposite. The gate is generated off the input signal, and the thing that's counted is from the master clock. So those signals have to be jockeyed around, and also some of the other signals associated with the gate and so on need to be finessed, and those are done through the essentially electronic switches built out of logic gates that are in here. And then the result of that goes into that chain of 5 decade counter ICs. They're the same kind of ICs that were used here and here. So these accumulate the count that's going to be displayed, and then on the transfer pulse, the count is transferred from all those ICs into all these ICs, which have a dual function. The first function is to act as a memory or latch, and the second function is to decode the BCD data in the latch or the memory in such a way that it can drive the 7-segment LEDs. And thrown into the bargain is that there's actually display drivers in there. So this is really a latch, decoder, and display driver, all 3 functions in these ICs. This transistor down here and the associated resistor amplify the transfer signal coming from this logic over here, so that it can drive all of these ICs here. Otherwise it may be not quite up to scratch in its ability to drive those, so it's beefed up by this transistor. And this transistor here is the one that in fact is driving the gate LED here. I don't think there's anything else to say about this. Oh, maybe I didn't show the back of the reset push button, but that's right here. One thing that I want to point out is there are a couple of inductors on here. This one here is part of a pi filter with these 2 tantalum electrolytic capacitors that provide a bit of noise isolation between the voltage regulator IC and a bus on the back of the circuit board that feeds all the TTL logic. But it's not the only circuit that has an inductor. There's also this one on the circuit board. It's just made out of circuit board foils. It's not that much of an inductor, but it has inductance, and that is from the same point. It's the output of the, if I can get these very stiff wires out of the way, it's the same electrical point as this, and it just comes down here. You can see it in the picture, and makes a number of windings, if you will, and then continues on to supply power to this front end circuit. Let's take a look at the Heathkit manual. So the manual styles changed a little bit from the ones I've been doing recently. all the IB series frequency counters where they've got the classic picture of the father swiping the screwdriver from his son who's trying to build a radio. I think he's not really swiping the screwdriver, but it kind of looks like that from the way it's drawn. So then they replaced it with this kind of two-tone photograph of somebody soldering a circuit board, apparently. It's really cheap compared to the old one. They should have left it alone. So we have the Heath telephone directory, the front page with the picture of the product and the table of contents. The introduction. The Heathkit model IM-4100 frequency counter is a versatile, easy-to-use solid-state frequency counter which can accurately measure frequencies to over 30 megahertz. The implied 30 megahertz is the highest that they actually guarantee, or the lowest that they guarantee. The counter is also a period meter and an events counter. The following features make this counter very versatile. Operates from 120 volts AC, 240 volts AC, or 12 volts DC. Combined power switch and time-based switch. Well, that's not really a feature. It's a space savings thing. 3-position mode switch. That's like putting automatic transmission on the rear of the hood of a car. Input attenuator switch. They're just listing normal features here. Overrange indicator. Reset push button. External time-based switch and connectors. They really aren't saying much about this product when it comes down to it. Excellent accuracy is assured by a modern digital design and a 10 MHz crystal oscillator. Additional features include a rugged and compact cabinet and a swing into position handle to elevate the front panel to a desired viewing angle. Exceptional accuracy, compact design, and the simplified operating controls combine to make this counter an invaluable tool for the engineer, technician, or hobbyist. So we start out with the parts list. Resistors, capacitors, cabinet parts, pictorial. The pictorials are just sort of jumbled in along with the actual parts lists themselves. Diodes, light emitting diodes, transistors, integrated circuits, sockets and connectors, hardware, lots and lots of hardware, switches, miscellaneous stuff. Printed material, assembly notes, which they always have in the front of every one of their manuals. We start building the display circuit board. It's the simplest and smallest. And I'd said earlier that the display board was connected to the main board by just bent pieces of wire, and that's incorrect. Heath did do that kind of stuff, but on this particular product, they actually used purpose-made pins for that purpose. You put those on, you put on the sockets for the LEDs, you mount the gate LED, cut up some ribbon cable to make the wiring bundles, then start assembling the main circuit board. Jumpers first. This is a single-sided circuit board, but it has a lot of places where they really needed to have double-sided, so they just put in a ton of wire jumpers on the top side. Start by low height components such as diodes and some resistors. More of the same. Putting in the IC sockets. More of the same. And then installing the ICs into the sockets. Installing the transistors. Installing the capacitors. Installing other things like the voltage selection switch, the fuse, the crystal, the large electrolytic capacitor, the trimmer capacitor, and then starting to solder wires onto the circuit board. Preparing more ribbon cables, soldering up the display board to the main circuit board, and inserting the pins on the display board into the main circuit board. Mounting switches to the front panel, cutting fish paper, mounting jacks and so on, and the push button to the chassis, mounting the front panel into the bezel and to the chassis, mounting feet, mounting the power connector, mounting the transformer, wiring up the attenuator switch and the other switches, some more wiring, continued, connecting the line cord, initial tests, initial test difficulty list and possible causes, final assembly, calibration without instruments or with instruments, operation, it's not counting the table here, it's only about 1 page of text. I think they really skipped some things that they should have put in here. A larger in case of difficulty and troubleshooting chart. Some important waveforms that might be referenced in the troubleshooting section. Specifications. I already mentioned those looking through Chuck Penson's book, so I won't repeat them. This is the table showing the input voltage derating curve. Circuit board description is about 1.5 pages. Circuit board X-ray views. Some of my notes that I've been making while studying the circuit. Semiconductor identification charts for diodes, transistors, and ICs. More ICs, and the 7-segment display module. And then customer service, and we're done. Well, we would have been done except for the separate fold-out sheet, which isn't bound into the manual. Some detailed figures, chassis assembly diagrams, more things having to do with calibration and testing. It's really an illustration book. There's a nice block diagram of the counter, a description of what things on the front and rear panel do, and a couple more assembly diagrams. Alright, here's the schematic. And it's kind of a mess, as I've been finding a lot of Heathkit schematics to be once I actually started studying them instead of just casually glancing at them. Neatly drawn, but often full of mistakes, not very well checked in many instances. A lot of issues, and that's one reason why I have a series of recreated CAD-drawn schematics where I attempt to fix as many problems as I can in the process. Okay, let's start this out with the power supply. AC power cord comes in, have the fuse, go through the one gang of the power switch, come back, you've got a capacitor across the line as a filter against high frequency noise. Primarily noise trying to leave this and go out, I think. Then you have the voltage selection switch, which determines whether the two primary windings are in series or parallel, and that will depend on whether it's 120 volts or 240 volt connection. And then the secondary is just a 10 volt AC winding, goes through a bridge rectifier, full wave bridge, if we're going to go with Electro Boom's enthusiasm for that. And then a filter capacitor, and into this same point comes the external DC power jack, which if something is connected there, then that flows through this diode and to the same point as the plus output of the diode bridge. So if you don't have this powered up, then there will be no voltage coming, or no current coming from here, no voltage developed, unless you input something here and it goes through the diode and provides that voltage and that current, of course. So then regardless of whether it's the AC source or the DC source, it still ends up being DC. Here is regulated to 5 volts by this 7805 voltage regulator. And for the impedance converter circuit, in other words, this one point up here in this circuit, we just use the 5 volts straight off the regulator. But for all the TTL logic, there's sort of a pi filter here with 2 capacitors and a inductor between them. So there really ought to be an inductor shown here as well on PC board foils. Alright. Anyway, so we have filtered 5 volts going into different loads on the circuit. Then we have the master clock, as already discussed in the internal views. We have a 2 inverter oscillator with a crystal in it. It's a classic circuit. These NAND gates are wired up as inverters, so you can just treat them as such. You've got one going through the crystal, comes out of the crystal, goes through the trim capacitors, goes into the next one, wraps around to the beginning, and then there's a resistor in the middle tying the feedback signal with this signal. That's a classic circuit right out of the textbooks. Nominally, the crystal will oscillate in this circuit at 10 megahertz, but you have these 2 capacitors here which help it get started and to run properly, and one of them has a trim capacitor around it, and by doing that adjustment you can force it to oscillate just a little bit higher, a little bit low from its nominal manufactured frequency, and by doing so you can tweak it to get exactly 1 mega or 10 megahertz out of it. Then the output of that is buffered with another inverter made from a NAND gate, and then it's fed into a decade counter which divides it down by 10, and you end up with a 1 megahertz signal here. Here is the switch on the rear panel for selecting internal or external oscillator, and assuming you've selected it to internal, then the master clock signal here just goes around, comes down, skirts around here, comes all the way around, and comes into the beginning of the 6 decade counter master clock stage. So it's a big counter made out of 4 decade counters, and this is the one that'll take 1 megahertz at the beginning, divide it down in orders of magnitude to 100 kilohertz, 100 or 10 kilohertz, 1 kilohertz, which can be tapped off of for use by the rest of the circuit, 100 hertz, 10 hertz, and 1 hertz, which is also tapped off for use elsewhere. Now, that 1 megahertz signal from the master oscillator can come over here and go out the jacks on the rear panel. If there happens to be a short circuit or something connected up here by some careless user, this resistor will limit the current to a safe level, so the fact that there's a short here doesn't mean that there's a short here, and the ICs will not be damaged. And in fact, the master clock signal will still go this way, it just can't go that way because it'll be through a resistor to ground. There's also a Zener diode here to limit the voltage here, and that's primarily a protection against signals which are input here, but regardless it limits it to whatever the voltage is on that, probably around 5 volts. The 2 outputs of the master time base scaler, as this is called, come up to the switch on the front panel, which decides if you're in kilohertz or megahertz time base mode, and then the result of that is either a 1 hertz or 1 kilohertz signal that's been selected, and it goes into one of the ICs that acts like an electronic switch. In this case, it's really just using these 3 gates as a buffer. It's not doing anything logically with them except inverting the signal, which isn't important, by the way. This IC is really set up to be used in this kind of combinational logic, and there are 2 nearly identical ones, each of them having 2 AND gates with 2 inputs each tied into an OR gate, actually a NOR gate, so you've got the inversion on the output. And there's 2 of them in there. Technically, this one is extensible using a couple extra pins on the IC, but Heathkit isn't using it that way, so you can ignore that. So again, the signal that's been selected comes through here, is just running straight through it, and because the other input to the OR gate is coming from an AND gate that has its inputs tied to ground, this is just a logic 0, so it doesn't do anything. The signal just passes straight through and then gets inverted on its way out. And then that wraps back into a round, and this here is used combinationally to select which signal source goes into this flip-flop. So normally the logic coming off of here is associated with the gate. So this gate down here is enabled when the function selector switch on the front panel is in the frequency counter mode. Thereby it allows the signal coming from the master clock that's been selected kilohertz or megahertz, coming back from here, to pass on through and go to this flip-flop, and then thereby generate the gate signal. But if you're in period mode instead of frequency counter mode, then it's the actual conditioned input signal that gets to go through and drive this flip-flop. And that ties into what I said earlier, that the difference between the frequency counter mode and the period counting mode, or the period measuring mode more accurately, is which signal drives the gate and which signal drives the counter inputs. If the master clock drives the gate and the input signal drives the counter inputs whenever the gate is open, then you have a frequency counter. But if it's the other way around, then you have a period measuring counter. So that is handled right there. Now, that's how the gate signal source is selected. Similarly, there's this other IC up here, which is set up as a multiplexer, so you can turn on one of these gates at a time through signals going into them, and then they will allow other signals to pass through to the OR gate and then continue on. So this top one isn't being used because all the inputs are tied to ground. This one here is set up to be turned on in the totalizer mode. This one here is set up to be turned on in the frequency counter mode. And this one is set up to be turned on in the period mode. If it's in the totalizer mode, it just takes the output of the input conditioning circuit and passes it through. But while we're in that same mode, this logic down here doesn't pass anything through for a gate, because in totalizing mode there is no gate. We're just counting without a gate functionality. If you're in frequency counter mode, again, this part of the logic is picking the master clock as the source of the gate, and up here it's picking the output of the signal conditioning circuit as the signal that would go through the counters. And if you're in the period mode, this should be based on the master clock, and in fact it is. So this is where these two ICs are where that reversal of gate and input sources is accomplished. I know it's kind of hard to see here and I'm going kind of fast, but we take the signal coming from the master clock. I'm just going to keep it simple here and say we're in frequency counter mode. So we have either the 1 Hertz or the 1 kilohertz signal, whichever one's been selected, and that gets passed on to this flip-flop. This flip-flop's job is to divide those signals in half. And the reason for that is you need a 1-second gate or a 1 millisecond gate. If you tap off the 1 Hertz signal from the master clock, this is 1 Hertz, you can take the reciprocal of that and see that from here to here, that's the period of 1 cycle, is 1 second. Likewise, if you have the signal from the 1 kilohertz master clock, the period of 1 cycle is 1 millisecond. Well, that's all well and good, but for the counter to work in measuring kilohertz, we need to have a 1 second gate. And if we're measuring megahertz, we need to have a 1 millisecond gate. Well, that's great. You say we have 1 second here and 1 millisecond there, but that's the whole cycle. We're actually trying to produce a pulse which is 1 second wide, not a cycle that's 1 second wide. So what we really want is just this, or this. How do we get that? Well, we divide the 1 second by half and get 0.5 seconds. Or you divide the 1 millisecond in half, you get 0.5 milliseconds. And the result of that is you get a 1 second pulse if you're in the kilohertz mode, and you get a 1 millisecond pulse if you're in the megahertz mode. So that's what that flip-flop here is doing. It's converting the selected master clock by half to get the desired width of a gate signal pulse. And indeed, I've marked up on my highly marked up schematic that that's the source of the gate. It's fed back to use in this under certain mode selections. Primarily, it operates this transistor, which provides a current path to ground through the gate LED, allowing it to turn on. And the flip-flop has 2 outputs, the Q and the Q naught. They're just complements of each other. So the Q is being used to drive the transistor that operates the gate LED, and the inverted version of it coming from the Q naught gets sent through this whole chain of gates and RC networks. When you see this configuration, a series capacitor with a resistor to ground or to V+, and then a gate following it, that's taking an edge and turning it into a pulse. So for example, here's the gate pulse. It's the inverted gate pulse, so it's going low rather than going high. So when the signal's rising back up here, that's at the end of the gate pulse, this circuit detects that and generates a short, low-going pulse right during that transition time, so a very short pulse. Well, that pulse is too short to be used by anything, or hardly anything, so there's a monostable multivibrator here, which stretches it out a bit so that it's more user-friendly by other logic. However, it is used in its raw state. Coming right here, it gets passed through this gate and continues on as the transfer pulse, and it goes through a transistor to get current amplified so that it can drive multiple things, and then it goes into all of the display driver ICs to tell their latch functionality it's time to take the BCD signals from the counters and store them in the latch memory. So that's one thing it gets used for. And then the stretched version of the transfer pulse gets edge captured again, and that generates this a waveform down here, and the untrimmed version of it also comes down, and they get combined in a gate. And that's all associated with what happens in certain modes, how you have to operate this. Normally you would just have these counters running free, but sometimes you need to force them, and that's what this logic does, to force it to behave a little differently. And that influences not only these counters, but through this gate it influences the flip-flop that's generating the gate signal. Can you guess when that's needed? Almost certainly the period function, and that's what it's being used in. Because it's not enough to just swap the two inputs for gate and counter input. You have to play a little bit of a game with this to get it to work out properly, and that's what these finessing functions are doing. And then finally, out of all this, you generate a clear pulse that's used to clear the counters before a new count is taken. We use it in its unmolested form as the reset pulse, and that resets the 5 decade counters for the display, and through its inverted form it resets a flip-flop here that I'm going to talk about momentarily. So the switched signal that's going to go into the counter comes around here, and it comes into the first decade counter. Least significance on the right, so we're feeding the signal to the left. You go through the first decade counter, that overflows into the second, overflows into the third, into the fourth, the fifth. If the fifth one overflows, that means you've overranged. So that signal comes around here and goes into a flip-flop. All that does is captures the fact that the most significant digit has overflowed, and thereby you're in an overflow condition. When we get the transfer pulse, all the BCD data from these counters is transferred up into the latch or memory function of the display driver ICs, and also this flip-flop that captured the overrange state gets locked in to this flip-flop that's made out of discrete NAND gates, so that it's stored similarly to the memory or latch functionality of these ICs. So really, this whole thing, this IC and this IC, in 4 gates of it, acts just like the next stage of the counter chain and the next stage of the latch or memory function. It's just that they're drawn over here, so it's a little confusing. If the latch here indicates that an overrange indication has occurred, that reaches all the way back up around here and energizes the decimal point at the upper left of the most significant LED display. And then that operates just like any other segment. It's just a common cathode display, so you can picture this being an LED connected from here to here, which goes to ground. The trick about this is that these displays normally have their decimal point in the lower right hand corner. We're only using one of them in that way. The others are not used at all. I mean, the decimal points are not used. In order to get this particular most significant display's decimal point at the upper left hand corner, Heathkit decided to insert it into its socket upside down. So all of the display is really upside down. However, the manufacturer of this LED module arranged the pins on the connectors. It's a row of 5 pins here and 5 pins here, which is not shown schematically here, but it works out that with the exception of segment G, which is the middle segment here, and the decimal point, everything is wired to opposed pins. So if you look at it this way, here's the pinout in the manual. It works out that the pins are opposite, so for example, F and C are diagonally opposed from each other. C is on segment 4, and F is on segment 9 here, and 4 and 9 are also diagonally opposed, and that works out so A and D swap, B and E, F and C. It's just G is the oddball, and it ends up at one corner and the decimal point at the other corner, so those don't get correctly swapped when you put the display upside down in the socket. And for that reason, Heathkit arranged the circuit board foils to compensate for that disparity. Okay, really only the remaining thing to talk about is the input circuit. So we have the input jack here, the BNC connector, and you have a total of 1 megohm of resistances going to ground, so it's got a 1 meg input impedance. It's got resistors with capacitors across them for high frequency compensation, and depending how you have the switch set, you tap off either here, here, or here in the attenuator. So no attenuation, or some attenuation, or some more attenuation in orders of magnitude. And you really shouldn't have very high voltages once you get down to this point, and you can't really, because once you go through this additional 1 meg resistor here, there's diodes clamping it to ground, so this point cannot rise more than about 0.6 or 0.7 volts above or below ground. All the remaining voltage is dropped in this resistor. So you really want to pick your attenuator appropriately so you don't have too much current going through here and too much power dissipated. And that's a good reason to start with the highest attenuation, the 100 attenuation, and then shift down until you start getting enough voltage here to operate this circuit sufficiently or adequately. So here's the FET that provides the high impedance, and it's a source follower, so it makes a copy of the input signal, but at lower impedance this transistor helps it to operate. And I had penciled in down here this foil inductor, but Heathkit already showed it up here, and between that and these capacitors, this rail here is filtered, and here are the 3 stages of the ECL line driver receiver IC. These operate with inverse signals, as you would if you're doing a transmission line, which is what this is really designed for, but they work well in this capacity. And essentially what you've got here is an amplifier followed by a Schmitt trigger functionality, so that you've knocked the voltage down to plus or minus 0.6 volts here, and then you've amplified it, and then it's been boosted to a known level now, and then it's turned into a nice clean square wave by the Schmitt trigger functionality. And because it's an ECL device, the voltage levels, besides being complementary, are also not voltage levels that TTL logic would recognize. Even though they're still within 0 to 5 volt range, they're just not appropriate between a logic 0 and a logic 1. So these two transistors level shift that signal, and it comes out of here as a TTL signal. And the rest is history. We've already talked about that. So that's the schematic.